Welcome to Talking Science Interviews. Matt Miller with you in Studio 4. Well, I'm very excited to continue this dive into the movers and shakers of science and space news that we're featuring on Talking Science on Tuesdays with Dr. Brad. Today, Dr. Matt Owers from Macquarie University is going to join me to chat about the Sami survey that was released a couple of weeks ago.
On Apple Podcasts, Spotify, Google Podcasts, and YouTube for over 550 episodes. This is Talkin' Science.
And Dr. Owers is joining me now from Macquarie University. Dr. Owers, thanks for a little bit of your time on today's Talkin' Science Interviews.
No worries. Thanks for having me.
Now, can you tell us a little bit about the Sami Galaxies survey? It started 7 years ago. What was the genesis of the idea?
Yeah, so actually it started back in 2013. And I guess the genesis of the idea is that we really wanted to understand why galaxies look the way they do. It seems like a pretty simple question, but actually it's really hard to answer. And so we had a number of ideas about how what galaxies look like. For example, we've all seen images of galaxies from the Hubble Space Telescope and other telescopes like that. And they all seem to appear pretty diverse. So we see a number of different shapes of galaxies. They have a number of different colours. So they can be blue or red. When we see very blue galaxies, that means they're actively forming new stars, for example. Or if we see very red galaxies, that means they haven't formed stars generally for a few billion years or so. So there's a diversity of characteristics that galaxies have. And our survey was all about trying to disentangle what causes that diversity. So in order to do that, we needed to use about 250 nights on the telescope with an instrument called Sami, the Sydney AAO Multi-Integral Field Spectrograph. We like our acronyms in astronomy, as you might be fully aware.
Yep.
So Sami it allows us to take what's called integral field spectroscopy. Now, integral field spectroscopy is essentially we take an image of a galaxy, but for each point in the galaxy, we have a spectrum. So a spectrum, you might be aware, is where we break the components of the light up into its different wavelengths, much like a rainbow breaks up the light from the sun into its different colours, but much more granular. And so that allows us to make many different measurements of galaxies and try and disentangle the diversity of the galaxies.
Now, some info has already been released over the 7 years of the study, which has led to dozens of papers. The release a couple of weeks ago was the third and final data set. What's it like to reach this point after such a long time with the Siding Springs telescope, with Sami, doing all of this analysis, as you say, over 250 nights on the telescope? That's almost a full year just in and of itself. So to finally see the end of it, how is that feeling?
Relief. It's a hell of a lot of work, as you pointed out. Just the nights on the telescope alone almost adds up to a year, but there's a huge amount of work that goes into analysing the data. Well, first of all, preparing for the survey itself. So the target selection to understand which galaxies that we want to look at, there's a lot of preparation work that needs to go in there. And our survey built off of a pre-existing survey called the Galaxy and Mass Assembly Survey, which is also an Australian-led survey conducted at the Anglo-Australian Telescope in Siding Spring. And that had 300-odd nights on the telescope previous to our starting of the Sami Galaxy survey. So on the shoulders of giants we stood and selected our targets. And that in itself took, we were doing that a year in advance easily of starting the survey. And then we start to talk about, analysing the data, making sure that we haven't got spurious artefacts in our data, and also analysing our data to sort of bring out the science. Is a huge investment of time across many, many different astronomers within Australia and also overseas. So I guess relief at that coming to an end, but also a bit of excitement because now we're moving into a space where we can start looking forward to the next big thing in terms of what we're going to do with the Anglo-Australian Telescope.
And I'm going to dive into that in a second. But with Sami, all of these nights, all of this data, it was analysing 13 galaxies at a time. I can only imagine the amount of raw data that you are confronted with as the analysis begins and gets underway. How do you make sense of all of that sitting in front of you?
Yeah, so that was a good problem to have. Having a lot of data is an excellent problem to have, but it was also a new problem because the 3,000 galaxies we had, each of those had its own sort of IF integral field spectroscopy data, which itself contains something like 1,000 spectra per galaxy.
Oh,
right?
wow.
And each of those spectra contains, almost 4,000 points of data. And so there's a huge amount of data to analyse there. And it's sort of it was a new realm for us to analyse that amount of data because previously we're used to having large surveys of several 100,000 galaxies even. But then we only have one spectrum per galaxy to analyse. So it's not easy, but it's easier to interpret the data because, it just led to a whole new level of complexity that we had to deal with. We didn't just have one data point per galaxy anymore. We had several thousand. And so, it was an embarrassment of riches to deal with. But you do need quite strong computational skills and computational power to do this in a human lifetime scale to analyse your data. Otherwise, if you're using computers from the 90s, we would never get through it.
Were there any surprises that came up in all the studies?
There were a few nice surprises. So I guess I'm completely biased. I'm going to talk about the stuff that I was surprised by.
Fair enough.
Previously, I mentioned that we had several other surveys previous to this where we had several 100,000 spectra of galaxies. So generally those spectra came from very central regions of galaxies. And so they told us about what's happening in the middle of a galaxy and didn't tell us much about what's happening in the outer regions. So for example, if we were, several thousand or several million light years away and turned around and looked back at the Milky Way galaxy with one of these surveys, we'd basically take a spectrum from the very central part of our galaxy that contains, a supermassive black hole and a spheroidal distribution of stars. But we wouldn't get any information about where we are as the sun in our solar system, sort of 8 kiloparsecs away from the centre of the Milky Way. So basically we received no information about that. So one of the things that I was interested in is looking at what the external parts of galaxies look like and how the external environment, we call it, influences the star formation, the formation of new stars in those outer parts. And what I was able to find is that when a galaxy zooms through a very dense region called a cluster of galaxies, where you have this sort of tenuous 10 million degree gas that permeates the space between the galaxies, what happens is a galaxy feels a wind, right? So it's like if you stick your head out the window of a car going at 100 kilometers an hour, don't do that. You feel a wind, right? It's all the air rushing past you. So a galaxy zooming through intergalactic space at sort of 10 million kilometers an hour also feels a wind because of this very hot gas. And it feels such a strong wind that it strips out any gas that galaxy might have.
Oh, wow.
And now what that gas in a galaxy normally does is it collapses and forms new stars. So once you take all that away, you stop the ability for a galaxy to form stars. And so what we were able to find was evidence for these galaxies that had recently fallen into a big, massive, sort of 1,000 trillion times the mass of the sun cluster of galaxies. And this interaction with the surrounding environment had stripped off the gas and stopped star formation there in the last billion years or so. So that tells us something about how the external environment influences how the galaxy produces new stars.
It is absolutely fascinating. that I think the best thing that I love as a bit of a facilitator for science podcasts, I don't have a massive background, or I don't have a background in researching this sort of stuff. Hearing from researchers and professors and everyone in the field about the amazing discoveries that come up with these galaxies, and how there's still so many things to be discovered, and even after Sami, there's still so much that can be learnt by galaxies. This isn't the be-all and end-all survey.
Absolutely, yeah. I think one of the amazing things that you may not often think about unless you're deeply embedded within this field is that galaxies change with time. I mean, it seems counterintuitive, like on the timescales that we are used to, sort of year-long timescales, galaxies don't change very much. But when you look at them in the context of the timescales that operate in the universe, 1 billion years is, not. It's a 13th of the age of the universe, but this is the sort of timescale that galaxies change on. And that's relatively fast.
And next up from Sami comes Hector, who is planning to do even bigger things with galaxies. Brad and I were talking about this a couple of weeks ago, that Hector is basically the equivalent of hold my beer.
Yeah. So Hector, we've doubled the number of objects that we can, a little bit less than double the number of objects that we can observe at the same time to take this integral field spectroscopy with. And we've also doubled the breadth of the region that we're able to see. So with Sami, I think our field of view was something like the size of the full moon. Now with Hector, we'll be able to double that angular extent. And so that allows us to probe many more galaxies at the same time across a larger area of the universe. And so we'll be collecting data for around about 15,000 galaxies for that survey.
That's incredible. That's over 4 times the amount of the Sami survey. Are you ready for, say, 10 years? How much time is that going to take? Is that a 10-year, 15-year survey?
So we're hoping to be on Sky for about 5 years, and we're hoping to get a larger allocation of time from the telescope time assignment committee. So basically the way we get our time is we have to write a research proposal saying, what we want to do, what new things we're going to discover, and we have to lay out there how much time we want, which is sort of, we need to calculate that based off of what we want to do. And so we're hoping to get a large chunk of each year's worth of time over the course of 5 years to do our survey. And so again, I think it'll be something like a 200 or 300 night survey, a lot of observing.
That's actually something that I hadn't thought of. Obviously, not everyone has their own massive telescope in the backyard or on campus at universities. So there are a limited number of telescopes and many research projects to do. So it is a bit of a battle, I guess, or is it a bit of a battle to get time on the telescopes, get enough time that you need?
Absolutely. I mean, so the Anglo-Australian telescope, for a 4-metre telescope, it's quite competitive. And the reason behind that is because we have very good instruments on there. So we've, as an Australian community, we've been very good at inventing new instruments to use to make use of our 4-metre facility. And a 4-metre facility nowadays is not huge in terms of astronomy telescopes. We have 10-metre telescopes, the Keck telescopes in Hawaii, the very large telescopes in Chile are 8 metres. So, those telescopes are very competitive, but the AAT does very well. So I think that it's called the oversubscription. So how many applications go in compared to how many get awarded time, it's around about a factor of 2 or so for the Anglo-Australian telescope. So you need to write a good proposal, and it needs to be compelling scientifically, and it needs to be feasible. So it needs, they look at it and say, well, actually, can you do that, what they claim they're going to do with our telescope or not? And so you're judged based off of that and awarded time or not.
Fantastic, Dr. Owers. It is always fantastic to bring scientists onto Trekzone and hear about the stuff that is happening in the community, especially from an Australian perspective. I think the best thing that I've learned here at Trekzone is that we punch above our weight in the space and science communities, and Sami and Hector are just further examples of that.
Very good. Thank you very much for your time, Matt.